When we're looking at hydrogenation, what that means is you're going to take an alkene, it's our double bond, and we're going to add hydrogen across it. Now the reaction needs a little bit of help, so we usually put a metal catalyst. So in this case, we're going to use palladium. Sometimes you'll also see palladium written like this, where it's palladium on carbon. Same idea. It just makes it a little bit easier to work with. There's other metals you can use, nickel, platinum, rhodium, but palladium's kind of the most common one. Now, what we're going to see in our product is the double bond disappear. So that would be your answer, cyclohexane. And what we've done is remove the pi bond of the alkene. Now the way this works is if you envision your metal, so let's put this as our metal plate. In this case it'd be palladium. What happens is it gets coated with the hydrogens. And then your carbon double bond comes in, and the pi bonds are exchanged for these hydrogens, and we lose this pi bond. And since the two hydrogens are added from the same face, what that gives us is a cis conformation. So in this molecule over on the right, our product, we didn't have to draw out the hydrogens because the hydrogens in the zigzag form are implied. But if we wanted to, we could have shown explicitly that they're cis by making them both wedged or both dashed. And we could add them from either face, right? Because there's no stereochemistry control in this one. Alright, so the take-home message from this is that when you have hydrogenation, so hydrogen and metal catalyst, you're going to remove any alkenes. Right? They're going to go all the way down to the alkane. And we'll see later that they can also do the same for alkynes. So they can typically take any carbon double bond or carbon-carbon triple bond all the way down to the alkane. Now typically, you just put a lot of hydrogen in. Usually you fill a balloon, you can even have a hydrogen tank hooked up to your reaction flask. And so unless it explicitly says you only have one equivalent to 1 mole, if you have multiple double bonds, you can hydrogenate both these. So in this reaction, we're still using hydrogen and a metal catalyst, so in this case palladium, and we're going to remove these two double bonds. So just start by drawing the carbon framework just the way it is, without the double bonds. Here's where our double bonds used to be, and they're gone. And so now you've completely erased the double bonds. Now if you wanted, you could explicitly show the two hydrogens you've added on the first double bond and on the second, but you don't have to in the zigzag form unless the question specifically asks you to show the hydrogens. But we just added all the hydrogens across the double bond, and this is how we can reduce alkenes. And sometimes you see this on food labels. Hydrogenated fats is this reaction here, where they add hydrogen across double bonds to take those unsaturated fats to saturated, because saturated means they have all the hydrogens they can hold.